Welcome back, everyone. Today is our second lecture looking at vapor compression and refrigeration units or cycles. We're going today to do an example on a vapor compression heat pump cycle, and this will be our last lecture not only on vapor compression, refrigeration, and heat pumps, but this will be the last new lecture of the course. So after this, we'll move to doing some review for the exam. Now, what's the difference between a refrigeration and a heat pump cycle? Remember, these are structured exactly the same. The difference is our perspective. If we were doing a refrigeration heat pump cycle, the energy benefit would be the heat that's coming into our evaporator from our cold reservoir. But since we're talking about a heat pump, where the goal of the heat pump is to heat up the hot reservoir, we're instead looking at the heat that leaves our condenser to heat up the hot reservoir. So the energy benefit here is going to be the heat transfer rate at the condenser, Q dot out or Q dot hot. Our cycle will look something like this, where our condenser condenses from saturated vapor down to saturated liquid. We go through this isenthalpic valve. Remember here, delta H is equal to 0. I've exaggerated probably how slanted this line ends up being, but I wanted to really make it clear that this is not an isentropic process with a vertical line. Then we move through our evaporator to increase the quality of our refrigerant at our low pressure, and then we'll increase the pressure through the compressor. So that's what our cycle looks like. Here I've drawn the energy terms that I think are important for each process. Through the compressor, I'm adding power into the system. In the condenser, I'm rejecting heat. In the valve, I've drawn this like a turbine where I'm producing power, but since this is isenthalpic, W dot will also be 0. And then I'm adding heat into the evaporator. So this is what my vapor compression heat pump cycle looks like. A TS diagram for a refrigeration cycle would look the same, but for the heat pump, my energy benefit is the heat rejected from the condenser. If I want to characterize the system, I'll still take the energy benefit divided by the energy cost. The energy benefit here is the heat transfer out from the hot side. That's the heat transfer from my condenser, divided by the net power. But remember, the net power is only the compressor power here because it's the only component in my cycle that has a surviving power term. If I was looking for the Carnot or maximum coefficient of performance here, typically for heat pumps, we'll use the Greek letter gamma. Here we have T hot divided by T hot minus T cold. Remember, because there's no delta T in the numerator, it's important to use absolute temperatures here, at least in the numerator. My advice is always, if we're doing Carnot efficiency or Carnot coefficient of performance, use absolute temperatures, because you'll never get the answer wrong if you use absolute temperatures. So for each component, we'll do an open system analysis. That means we'll have to draw a control volume, we'll do conservation of mass, we'll do conservation of energy, and then sometimes we'll have to think about what the second law looks like for this particular component. And even if we're not doing this explicitly, we have to really understand that when we say a process is isentropic, we're really doing a second law analysis, saying that the process is steady state, that it's adiabatic, that it has one inlet and one outlet, and that it's ideal. So this tends to be true for compressors, turbines, and pumps. So these steps will give us symbolic solutions. But then we'll need to ask, what's the fluid, so that we can fix the states, and once we've fixed the states, then we can get numerical answers for things like coefficient of performance of our heat pump. Conservation of mass, hopefully this is no surprise at this point, looks like this. We'll often assume that components are at steady state or that there's one inlet and one outlet. Remember, these are common assumptions. It doesn't necessarily mean we're going to use these assumptions all the time. If we were doing a first law on an open system, we might assume that it's at steady state that there's one inlet and one outlet, that there's no change in kinetic or potential energy, that it's adiabatic, passive, or maybe both. If we have a valve, we'll often assume that it's isenthalpic. Remember, that means delta H is equal to 0. And throughout our cycle, we'll generally assume that there are no friction or heat losses in the system. If we do a second law analysis, it looks like this. Remember, this entropy generation term needs to be positive for a real process, and it's equal to 0 in the ideal case. If this is ever negative, you know for sure that that's something that can't happen, and we can't even approach that performance. From the second law, we'll assume often that components are steady state, that they have one inlet and one outlet, and that they could be adiabatic. So then we'll get to the question, what's the fluid, right? Because the symbolic solutions are great, and I've said multiple times that this is kind of the 80% of the benefit that you get from doing 20% of the work, but ultimately you do want a numerical answer for an exam problem, so you'll have to know what's the fluid and how do you find things like delta H and delta S for a particular fluid. In this case, the fluid is going to be a refrigerant. Now, because this refrigerant is moving back and forth across the vapor dome, because it's evaporating and condensing, we'll fix states in a similar way than we would for a Rankine cycle. But we learned a new way to fix states for these refrigeration cycles graphically using a pH diagram. If we were doing a cycle where our working fluid was ideal gas, we would then have to ask, is it constant specific heat or variable specific heat? And then typically, to solve the problem, we'll try to identify where the isentropic processes are, because then we'd be able to use the isentropic relationships for ideal gases. So how do we find H or delta H in refrigeration tables? Today, we're going to go through a problem where we're using the SUVA charts, which you'd find in the FE handbook. So if you were going to write the FE exam, then you'd have to use this graphical method to fix all the states. You can also use the refrigerant tables that you can find in the textbook. If you have an ideal compressor, you'll find delta H in such a way that delta S is equal to 0. But then, if you'd like to know the exit at the real compressor, you might have to use the compressor efficiency. Remember that the ideal compressor consumes less power than the real compressor. And then in this case, you'll also have this isenthalpic valve. So it's not hard to find H at the outlet of the isenthalpic valve if you know the inlet, because the inlet specific enthalpy here is equal to the outlet specific enthalpy. That's what the definition of isenthalpic is, that delta H is equal to 0. If we're trying to find delta S, we can use basically the same methods. But we do have to remember, for that isenthalpic valve, delta S is not equal to 0. If it was a turbine, we would start by saying that it's isentropic, and then we would use a turbine efficiency. But for the valve, there will be a delta S, because really we're setting delta H to be 0. We can find the difference in delta S graphically if we're using the SUBA chart. So today, we're going to solve the problem using one of these pH diagrams. So we got to remember that this is sort of a scale version of a vapor dome. But it's not just a vapor dome here. We've got all kinds of information on this chart. If you want a review of how to use this chart and how to read it and where the different lines for different properties are, check out last class where we did the introduction to heat pumps and refrigeration cycles. So here's our example. We have a heat pump. Our heat pump is a traditional heat pump with these 4 components that we've been talking about. We know what the heat transfer out at the condenser is. This is in BTU per hour. So remember, this is in imperial units. We know T2. We know that we have a saturated vapor going into our compressor. We know T4 is equal to 0 Fahrenheit. And we know that T3 is equal to 110 Fahrenheit coming out of the condenser. We're asked to find the mass flow rate through the system, the power consumed by the compressor, the efficiency of the compressor, and the coefficient of performance of the entire system. So let's get to work. First, let's fix the states. So here, I'm looking at 200 psi. I know that this is the high pressure in my system, or the pressure across my condenser. I'm also told that at the inlet to my condenser, which is the outlet of my compressor, I have a temperature of 180 degrees Fahrenheit. So what I did was I found this 180 degree Fahrenheit line. I drew this here, and I look for the place where these two lines intersect. Because here, temperature and pressure are independent intensive properties, so where they meet is where I put my state point. So I know where state point 2 is. So next I'll find the state at the outlet of my condenser. Here I know that the temperature is 110 degrees Fahrenheit, but I don't have that on my table or on my chart here. I have 100 and 120. So here these look to be fairly linear, these lines, so I'm going to go halfway in between. So that's 110 degrees Fahrenheit, and now I've fixed state 3. So you can see we can do this relatively quickly, certainly more quickly than we do when we look up states in the textbook when we're doing linear interpolation. So next, I've got to find states 1 and states 4. So these happen at 0 degrees Fahrenheit. So first, I'm going to use the fact that as I go through the valve, it's an isenthalpic process. Isenthalpic processes mean that delta H is equal to 0. Remember, H is on my horizontal axis. So if I keep H constant, then I move vertically down until I intersect with my line at 0 degrees Fahrenheit. That gives me state 4. Now I know that at state 1, I had a quality of 1, so I had saturated vapor. So I'll put state 1 at this same temperature, because here as I'm evaporating my fluid, as I'm going from whatever quality we have here at state 4, it looks to be somewhere around quality of 0.4. But here I know that I'm adding heat, I'm evaporating my fluid, so the temperature remains constant. Now the quality at state 1 is equal to 1. I have a saturated vapor. So now I've fixed all the states in my real cycle, but the problem also asks me to find the compressor efficiency. I can't do that without the isentropic outlet of the compressor. So this is the part that I find the trickiest, to draw a constant entropy line, right? Because as I go through the ideal compressor, because the compressor is at steady state, adiabatic, one inlet, one outlet, and ideal, it will also be isentropic. So now I have to draw a constant entropy line. So you see the constant entropy lines are these ones that are slanting over here, but the slopes are changing, right? So the slope of this constant entropy line is different, right? So here's one constant entropy line, and here's another one, and the slopes are a little different. So I've got to draw a line that kind of splits the difference on those slopes, and it's a constant entropy line that goes up, and state 2s will be somewhere in between those two lines, right? If I took state 1 to be halfway in between these lines there, then it would be halfway in between these constant entropy lines up there too. So here's my constant entropy line, and I'm going to put state 2s. I'll draw this as an open circle to remind myself that it's the isentropic outlet. So I'll put that over here. Notice that as I move through the real compressor, my entropy increases, right? So I'm going from over here to over here. So I've moved to the right here, and I've increased my specific entropy going through the real compressor. Now I've fixed all my states. So I know that what I'm going to need is the specific enthalpies for all of these states, all 5 of these states. So now, if I take all of these states, now the nice thing about doing this on the computer is I can just get rid of all those other lines that I had. Again, I'm gonna recommend to you to bring some colored pencils to your exam so that if you have to fill out one of these charts, you can draw different lines in different colors. Because now what we're gonna have to do is drop vertical lines from each one of these points and read off the specific enthalpies. So if I do that from state 3, I get this vertical line that goes through state 3 and through state 4, and I'm going to say that hits this axis at around 45 BTU per pound mass. I know that I'm losing some accuracy whenever I do something graphically, but this is a way where I can fix these states relatively quickly. Next, I'll do the same for state 1. Here, I'll say that this vertical line hits this axis at pretty close to 100 BTU per pound mass. State 2S hits at about 120 BTU per pound mass. And state 2 hits at about, I'm going to say 133 BTU per pound mass. Now remember, I could get more accurate readings if I do linear interpolation in the table. But I can't mix graphical specific enthalpies that I get from this chart with enthalpies that I fix from the table. If I do, I'll get bad answers because the 0 point for the specific enthalpy on the table is not the same as the 0 point for the specific enthalpy on the chart. So it's different, right? So if I'm going to use the chart, I got to use the chart all the way through the problem. And if I'm going to use the tables in the textbook, I got to use the tables in the textbook all the way through the problem. And that's what I've done here. I've found all 5 of my specific enthalpies, although 2 of them are the same. So I guess there's only 4 specific enthalpies, even though there's 5 states. So now we want to start to use the first law to get symbolic solutions for my problem. If I was on an exam, I would probably recommend doing this part first, because like I said, it doesn't take as much time as fixing states generally, and you can demonstrate that you understand how to do these thermodynamic problems reasonably quickly, even though you won't get a numerical answer just from getting the symbolic solution. We'll start with the condenser. We know the condenser is at steady state. We assume that it's one inlet and one outlet, that we can neglect changes in kinetic and potential energy, that it's passive, there's no fan blades on the inside, that there's no friction losses or heat losses as we move through our condenser. When we do that, we get that the heat transfer rate from 2 to 3, this is the heat transfer rate that's our energy benefit in this case, is equal to the mass flow rate through the system multiplied by H out minus H in, or H3 minus H2 in this case. So if I want m dot, which is one of the things that the problem asks me for, I look for the component where I know the heat transfer rate. In this case, that was the condenser. Remember, the problem told me what the heat transfer rate was. So now I can get an expression for the mass flow rate here that its Q dot is equal to H3 minus H2. Here, I put numbers in, and now remember, I gotta watch the units here. So here, I have a mass flow rate of negative 60,000 BTU per hour divided by 45 minus 133 BTU per pound mass. So the good thing here is that I'm going to get a positive mass flow rate. That should always happen. If I got a negative mass flow rate, I think technically what that means is that the mass flow rate is flowing in the opposite direction that I think it's flowing. So here I have a negative divided by a negative, but I'm going to get this in pounds mass per hour. And maybe that's how I want it, but maybe I'd rather have pounds mass per second, so then I would have to convert from hours to seconds. But in this case, I'll just leave it as pounds mass per hour. Next, we'll do a first law analysis on the compressor. Here, we assume that it's at steady state, one inlet, one outlet, no change in kinetic or potential energy, that it's adiabatic, so I can cancel out that Q dot term, that there's no friction losses and no heat losses across the compressor or between the compressor and any other component. So now, the power consumed by my compressor is given by m dot times H1 minus H2. The good news is I already figured out m dot, and now I have m dot times H1, which I know, solved graphically, and H2, which I also solved graphically. So here I get an answer of negative 22,473 BTU per hour. So I'm getting a power that's energy per unit time. So that's good. That's what power is supposed to be. I'm also getting a negative power, which is what I would expect when I'm talking about a compressor, which is consuming power. But if I went to the hardware store and tried to buy a compressor that was in BTU per hour, I think I'd have a problem. So what I'm going to do is I'm going to divide by 2,545, which is the conversion to go from BTU per horsepower. So there are 2,545 BTU per hour per horsepower. So when I do that, I get that my compressor power is negative 8.83 horsepower. Now, as engineers, we recognize that that negative number means that the compressor is consuming power, but you're never going to find an operator's manual of a compressor that says that it has negative horsepower, right? So we have to remember that, when we're sourcing different components, we don't include the negative sign here, right? So now we can find the compressor efficiency. We know that the ideal compressor consumes less power than the real compressor because that power consumption is a cost, and the irreversibilities in the system increase the cost that we have to pay. So now I know all these specific enthalpies because I solved them graphically. They're all in the same units. So this is going to be a dimensionless number. And I get that the compressor efficiency here is 60.6%. Finally, I'm asked to find the coefficient of performance. Here, my coefficient of performance is given by gamma. It's going to be Q dot on the hot side divided by the energy cost, which is the power that I have to put into the system, so the net power. But of course, the net power is just the compressor power because the valve doesn't produce any power. I can divide both of these terms by the mass flow rate and get little q dot over little w dot. In this case, right, I've included the valve power in my original expression. I was just given q dot, so I don't have to work on this sort of symbolically first. I was just given the value here. I know that the power for the pump, which I could actually just put in as the power, right, because I just found that. And then w dot valve, I included in my net power. But I know that that valve power is 0. So I get 60,000 BTU per hour divided by 22,473 BTU per hour. These are both negative, but if it was a refrigeration unit, one would be negative. That's the power would still be negative, but the heat transfer term would be positive. So these coefficient of performance are also always going to be absolute values, even though this one works out to be positive anyway. So here, I get my actual coefficient of performance is 2.67. Remember, this is why we call them coefficients of performance and not efficiencies. Efficiencies can only go between 0 and 1. It's not sports. You can't have more than 100% efficiency in a turbine or in a thermodynamic cycle. So here, because we have numbers greater than 1, we're calling these coefficients of performance. So that concludes our example for heat pumps. It also concludes all the new material that we'll cover in this thermodynamics course. So if you got to this point, we're almost done. Right? Now it's going to be about preparing for the exam by doing reviews. So you can do that by just checking out other videos. So there's the long lectures, or you can look at the cycle analysis problem. So basically I've broken down each individual cycle and made a video for that. So you can check out that playlist on my YouTube channel as well. We'll in class, if you're taking this class with me, we'll do a series of review lectures. So typically, instead of me just lecturing to you, what I like to do there is have students bring in problems that they have or sort of suggest different types of problems for cycles that they find difficult, and we'll do them together on the board or virtually in the world that we live in 2020. So thank you. I appreciate going on this journey with you, and I look forward to seeing you in a review lecture if you're taking the class with me, or if you're just doing this virtually. Good luck as you approach your own exam or your FE exam. I know that you'll all do very well now that we've gone through this course together. So thanks for sticking with me through this process. See you next time. Bye-bye.